Welcome to lecture number 20 of PH 4105, Advanced Mathematical Physics, where we are currently talking about differential geometry. So far, we have essentially met two kinds of objects on a differentiable manifold. We have met vectors, also known as tangent vectors, which belong to a particular point P of the manifold M, and their set is what you call TPM. If you take the union of all the TPMs together, you get the tangent bundle Tm of the manifold M. In addition to vectors which live on the tangent plane of a manifold, you also have covectors, which are basically dual vectors, objects which map these vectors into numbers in a linear fashion. And such covectors, also known as dual vectors of course, together form a set called Tp star m. These are all duals to vectors at the point P. And the union of all the Tp star m's give us what is called the cotangent bundle T star m. And once you have the tangent bundle and the cotangent bundle, you can introduce the concept of vector fields or covector fields. These are maps from M to either Tm in the case of vector fields or M to T star M in the case of covector fields. But the important point is a point P gets mapped onto a vector by, say, this vector field X, which belongs to TPM. Similarly, a point P gets mapped by a covector field alpha to alpha P, which belongs to TP star M. In other words, these vectors that a vector field returns at a particular point are tied to that point, and the same thing can be said about covectors. This was a quick recap of the kind of objects that we have met so far in our course, and we are next going to talk about a very important class of objects that we have all heard about, the so-called tensors. We will begin by talking about a particular kind of tensor, a 0k tensor, or a tensor of type 0k, something for which the older name, which is still prevalent, is a covariant tensor of rank k. This is also an object which is local, is tied to a point P of the manifold M. And a tensor is nothing but a multilinear map. It's a map which takes a bunch of vectors, exactly k vectors, into reals. So, domain of Tp is TPM cross and so on, cross TPM. K times different TPMs are getting Cartesian producted here. What that essentially means is that domain consists of k vectors or tuples of k vectors. And the range is a set of real numbers. What is important in addition to this is the demand of multilinearity. What that means is when Tp gets to act on a bunch of k vectors, one from each of the TPMs, and if one of those vectors have been written down as a linear combination, AVP plus BWP, where VP and WP are members of TPM, are actually vectors stuck to the point P, and A and B are real numbers, then the number you get as a result of doing this is basically A times TP acting on VP, where all the other arguments stay the same, whatever were here and here, plus B times TP acting on WP with all the other arguments the same. Now, we have already seen a linear entity, a map which maps vectors into numbers linearly. That is, of course, a covector. But it takes a single vector as an argument, so a covector is really a tensor. It's a 0-1 tensor, or a covariant tensor of rank 1. So we have already met tensors before this, and we have also met another kind of tensor before this, a 1-0 tensor, the so-called contravariant tensor in the old language. We are going to talk about that later. But it should be pretty obvious what a 1-0 tensor is. That's nothing but a vector. Now, in a sense, we can actually say a tensor is a vector. I'm not talking about a 1-0 tensor, I'm talking of all tensors. And we can say quite legitimately that a tensor is nothing but a vector. The first time I saw this written down, I guess it was in Larry Gilmore's textbook on Lie groups and Lie algebras. I was pretty shocked by the statement, because after all, we all study different classes of quantities. We start with scalars and vectors, and then we learn about other quantities like tensors and so on. So a statement like a tensor is a vector might seem quite shocking. But what this really means is a set of all 0k tensors tied to a point P, something which we denote by TP0km, form a real vector space. So tensors are elements of a real vector space. So in that sense, they are actually vectors. Of course, when you say they form a real vector space, I have to define how you add a tensor to another, and also how you multiply a tensor by a real number. So let's define them together in one go. If A and B are real numbers and TP and SP are both 0k tensors, then you define ATP plus BSP, this linear combination, in a very obvious fashion. Remember, tensors ultimately are multilinear maps which map k vectors into numbers. So, in order to figure out what this is, let's deal with something we understand better. We of course understand numbers more than we understand tensors. So to change this into a number, we are going to give it k different vectors as arguments. V1, P, V2, P, VKP. The P's here just indicate that all these tangent vectors are actually tangent to the manifold at the point P. Now we define ATP plus BSP in this manner, that acting on k such vectors, the result that you get is A times TP acting on those vectors plus B times SP acting on the same set of vectors. Now, if you think about it, this is actually the most obvious way in which you could define linear combination. And it is very, very easy to check that once you impose this definition of how to linearly combine two tensors of rank 0, k each. Of course, each of these tensors have to have the same kind of type. They both must be 0k tensors, because otherwise you will not be able to feed the right number of vectors into TP and SP respectively. But once we have that, if we confine ourselves to the same rank tensors, all of them 0k, it's easy to see that this is a well-defined tensorial object. Not only that, this combination obeys all the basic demands that you have for a vector space. Now, in order to prove that this is a well-defined tensor, what you really need to show is that this maps k vectors into numbers, but that is what the definition obviously does for you. But you also have to prove that this particular thing is multilinear. That is, if you were to replace any one of these k vectors by a linear combination of two or more vectors, the result would become a linear combination of their corresponding results. It just takes a bit of writing the thing out to prove this. It's really rather simple, so I'm not really going to spend more time on that issue. But there is another way of combining tensors rather than linearly combining them, which is a bit novel and which will be of great usage later. Now for this, you don't need your tensors to be of the same rank. You could take a 0k tensor and a 0L tensor. A TP is a 0k tensor. SP is a 0L tensor. They are both tensors at the same point P. And you can form a tensor product. TP, tensor product SP. You can call this TP O cross SP if you want a quick way of talking about it, that's the symbol that we are using here. Now you define it in a particular manner. You define this to be a 0 k plus L type tensor. Again, in old language, a covariant tensor of rank k plus L. This means, of course, that we have to tell you exactly what it does when it's given k plus L vectors as arguments. So TP tensor product SP, given this k plus L arguments V1, V2 up to Vk plus L, all of them at the point P, is simply defined to be the following. The first entry of the tensor product, this first factor, so to speak, TP, gets the first k of the vectors in the argument list. SP gets the next L, those numbered from Vk plus 1 to Vk plus L. And both of these, of course, return numbers. You just multiply these numbers together to form TP direct product SP's action on k plus L input vectors. Now, this, of course, gives you a map which acts on k plus L vectors and gives you a real number. So it is a map tentatively of the kind of 0k plus L tensor. But in order to check that it's tensor, what you need to really prove is that it is multilinear. But that is a very easy thing to prove. The only thing you have to be careful about here is when you change one of the input vectors to a linear combination, it will be either one of the first k or the next L. So either TP will get it as an argument or SP will, never both at the same time. And from that point on, once you appreciate that, the rest is going to be very trivial to check. So this really is a k plus L rank covariant tensor. Now, some properties of the tensor product are going to come in very handy. And because tensor products are not so well known, at least they may not be so familiar to you, I would like to talk about them in some detail. One important property is that the tensor product is distributive over this addition or linear combination of tensors. So if you have T1, T2, two tensors, I'm not going to say T1P, T2P simply because we are going to assume that the P is there always. Just like you can't add vectors stuck to two different points because they belong to different vector spaces. You cannot really add or linearly combine tensors at two different points. So all these are tensors at a particular point, P. I'm just not going to say P all the time. So if you have AT1 plus BT2 and you form a tensor product of that with S, of course all of them at P, what you get is a k plus L tensor, covariant k plus L rank tensor at the point P. And just to see what that is, you have to give it k plus L arguments. Here I have not even written V1P, V2P, etc. I'm just assuming that the fact that these are vectors at the point P is sort of obvious. Now what happens here is, this first factor of the tensor product, AT1 plus BT2, it gets the first k input vectors, S gets the next L. But here, by definition, AT1 plus BT2 acting on V1 to Vk is AT1 acting on V1 to Vk plus BT2 acting on V1 to Vk. And now these are just numbers. This is just a real number, so is this. This is also a real number. So here we are dealing with simply real numbers for which the distributive law is something we all know. A plus B into C is AC plus BC, where A, B, C are numbers. That's exactly what we are going to use here. We are going to open out the bracket, which essentially means we are using the distributive property. And this combined together with the weights A and B give you the result. But notice that this thing up here is nothing but T1P direct product SP acting on these k plus L vectors. And this thing down here, apart from the B, the rest of it is nothing but T2 tensor product S given the arguments v1 through vk plus l. Or by the definition of how you linearly combine tensors, this is nothing but this combination AT1 tensor product S plus B T2 tensor product S acting on these arguments. Now these arguments can be any bunch of k plus l vectors you want. And since it works for any k plus l vectors, it means that the two tensors that you have here, which are acting on those k plus l vectors, this here and this one here must be one and the same. In other words, AT1 plus BT2 tensor product with S is AT1 tensor product S plus BT2 O cross S. The distributive property. Well, what we have shown is that a sum on the left distributes. What remains to be shown is that if the second factor had been a linear combination, it would still have distributivity. Tensor product is not just left distributive, it's also right distributive. But that is very simple to prove. The proof is exactly similar to what we have done so far. So I'm not going to talk about that in any detail. If you want some practice, you should actually go ahead and try proving this particular result that you can see on your screen right now. The proof, of course, is very similar to what we have already done. We next turn to another property of the tensor product which makes dealing with it much simpler than it otherwise would have been. This is the property of associativity. If you have three tensors, R, S and T, each at the point P, which are respectively of type 0k, 0l and 0m, then can form a tensor product out of all three, either by doing this, which is forming the tensor product of S with T first and then taking R's tensor product with that, or this, where you take the tensor product of R and S first and then take a tensor product of T with that. These, of course, are both K plus L plus M rank covariant tensors, or basically 0 K plus L plus M tensors. The question is, are these two the same? That is the tensor product really associative? Of course, the heading here says that it is, but we need to prove that it is true. To check whether it is true, what we need to do is to feed both of these K plus L plus M vectors to get to a number finally. Of course, all of these K plus L plus M vectors would have to be at the point P. And check whether the two numbers you get in these two different ways are the same or not. Well, according to the definition of the tensor product, this thing acting on a bunch of K plus L plus M vectors works in this fashion. Rp, the first factor, gets the first K vectors in this list, and SP tensor product Tp, SPO cross Tp, gets the rest, that is vectors number, K plus 1 through K plus L plus M. Well, using the definition of the tensor product once again, this quantity here is nothing but SP getting the first L of these vectors, that is Vk plus 1, Vk plus 2 up to Vk plus L, times Tp getting the rest. So basically, when you take this tensor product and feed it a bunch of K plus L plus M vectors, Rp gets the first K to produce a number, Sp gets the next L to produce a number, Tp gets the final M to produce a number, and these three numbers are then multiplied together. Let us look at what happens when you take this particular tensor product with the brackets in a different place and feed them the same bunch of K plus L plus M vectors. Well, here Rp cross Sp, which is actually a K plus L rank covariant tensor, that eats up the first K plus L vectors of the list. You have to multiply that result, which is just a number, by Tp acting on the rest of the vectors. But now, use the definition of the tensor product once again, and this becomes Rp getting to eat the first k of these vectors and Sp getting to act on the rest, which is L of these vectors here, Vk plus 1 through Vk plus L. And of course, finally, you have to multiply all these three numbers together and check this is exactly the same as this. In other words, these two possibly different tensor products, they could have been different for all you know, turns out to produce the same result when given the same input vectors, no matter what input vectors you give them. Therefore, they must be the same tensor, and therefore you must have this result. That the tensor product is associative, which is just another way of saying that you can write the tensor product without actually putting in a bracket. So you can write this as Rp O cross Sp O cross Tp. Since the product is associative, it makes sense no matter which one of these tensor products you carry out first, there is no need to put in a bracket. We will now make use of these properties of the tensor product to find a representation for a tensor at a point, given that your manifold has a coordinate system. So we are going to look at coordinate representations of tensors now. Since tensors are, after all, maps which take in vectors and produce numbers, let me quickly remind you what a vector looks like once you have a coordinate system. Once you have a coordinate system, a chart u, phi, with coordinate functions x1 through xn, the tangent plane has a very natural basis, something we have talked about earlier. The basis provided by the tangent vectors to the coordinate curves, del xi p. So Vp turns out to be a bunch of numbers multiplying these basis vectors, Vp xi, del xi p. This thing that we spent quite a lot of time demonstrating earlier shows not only that the del xi p is actually form a spanning set for TPN, it also gives you a direct way of calculating the coefficients. But notice that our definition of a differential of a function at a point P tells us that this Vp acting on xi is nothing but the action of dxip, the differential covector at the point P, acting on Vp. This is just a definition of dxip. Acting on Vp, it provides the result which is equal to Vp acting on the function xi. Now, if you use this and think about what Tp does to a bunch of k vectors, of course it produces a number, but the number can be rewritten in a rather illuminating fashion. V1 can be written as dxi1p acting on V1, that's the i1th component of V1, times del xi1p. Of course, the sum over i1 is always implied here, and so on until the kth vector will be written down as dxikp acting on Vk del xik of P. Now, what is important here is that the tensor is multilinear. So, the tensor can actually go and act only on the vectors here, with the numbers just coming out of the tensor action. The numbers, remember, are these, and these. So, this number, Tp acting on V1 through Vk, is actually the same as Tp acting on del xi1p, del xi2p, all the way up to del xikp, times dxi1p acting on V1, dxi2p acting on V2, and so on, right up to dxikp acting on Vk. Now, this final piece, according to our definition of the tensor product, and also using the fact the tensor product is associative, can be easily rewritten in this fashion. You can write this whole thing as dxi1p, dxi2p, dxikp's tensor product. Remember, you don't have to specify where the brackets are because this product is associative. Acting on v1, v2 up to vk with this as a coefficient. So Tp, I1, I2, Ik is nothing but what Tp gives you when you feed it the coordinate basis vectors del xi1, del xi2, etc. in that order. Now, this of course is not a single number. These are n possible numbers for each of the indices. So n to the k distinct numbers defined, as I just said, as Tp acting on the coordinate basis vectors at the point P in that particular order. These are what we call the components of the 0k tensor Tp in the coordinate system. By the way, when a physicist defines a tensor, she typically talks about these n to the k numbers, these components, as describing the tensor. Of course, these components depend strongly on the coordinate system. And the physicist's version of a tensor's definition involves how these numbers change when you change your coordinate system. The differential geometric definition of tensors is actually much simpler. It's just a machine which takes k vectors and changes them linearly, multilinearly into a single real number. Much simpler and more elegant, definitely, than a bunch of n to the k numbers which transform in a particular manner. In fact, the transformation law is also something which follows immediately from the definition that we have written down here. But before we get the note, this is something I just said, the Tp acting on v1 through vk produces the same result as Tp I1, I2, Ik, dxi1p, tensor product dxi2p and so on, tensor product dxikp acting on v1, v2, vk. And this works for all vi's. And given that, we can simply say Tp is the same as this Tp I1, I2, Ik, dxi1p, dx product dxi2p, etc. This tensor product of k coordinate differentials form a basis. Of course, there are n to the k such distinct possible tensor products. And that forms a basis of the n to the k dimensional vector space T0kPm. Now, we were talking about coordinate transformations. And that is, of course, relevant only if you have two different coordinate systems to talk about. So you can talk about this only in the overlap region u intersection u prime of a domain of two coordinate charts u, phi and u prime, phi prime. Let's say the coordinate functions corresponding to u, phi are x1, x2 up to xn, and the coordinate functions corresponding to u prime, phi prime are x prime 1 up to x prime n. Then, using the chart u, remember we are in the overlap region, so you have the full right to use either the chart u, phi or u prime, phi prime. If you are using the chart u, phi, you will end up with this representation Tp I1 I ik dx I1p tensor product dxikp, or another representation where instead of dx I1p tensor product dxi2p etc. you use dx prime pj1 tensor product dx prime pj2 and so on, with of course a different bunch of components. Question is, can we relate these new components of tensor, components in the coordinate chart u prime, phi prime, with these original, quote-unquote original components? And the answer is rather simple. We know how to figure out these components. We have just worked it out. T prime p I1 to Ik is nothing but Tp acting on the coordinate basis vectors del x prime I1, del x prime I2, etc. right up to del x prime Ik, all at point P, all basis vectors according to the chart u prime, phi prime. But Tp itself can be written in this particular fashion: Tp J1 J2 Jk dx J1p tensor product dx J2p etc. tensor product dx Jkp. This is nothing but the representation of a tensor in the original u, phi coordinate system. Now, from what we know about a tensor product, all we can figure out is that this is going to be exactly the same as Tp J1 ... Jk, then dx J1p acting on del x prime I1, dx J2p acting on del x prime I2p. All of these are just numbers. This one is a number, this one is a number, and so on. And you multiply all these numbers together. Now the values of these numbers can also be written in a slightly different fashion. Dx J1p acting on del x prime I1p is by definition del x prime I1p eating up the function x J1. And shorthand notation for that is del x J1 del x prime I1. You must be pretty tired of me saying this over and over again, but let me stress once again that this is really not a partial derivative, because the x's are really not functions of x primes, but the proxy functions for x's, when you differentiate that with respect to the I1th coordinate function, you end up with these numbers. But since we describe the change of coordinates essentially by means of the proxy functions directly, this is exactly what we usually see these functions as. We think of these as actual partial derivatives. We are really going to do partial derivatives of the proxy functions, but the proxy functions are what we express these transition functions from one chart to another by. So finally, the transformation rule becomes the following. T prime p, the I1, I2, ikth component of that, is basically a linear combination of all the components in the original frame Tp, J1, J2, Jk, combined with these factors. Now these factors should be pretty familiar. If you think of the way in which a covector transforms, you would get del x j del x prime I as a single factor. Here you have a bunch of k such factors. Now this transformation rule is often used to define covariant tensors in the physicist version, as we have already said. But this actually follows automatically from the basis definition of a tensor as a multilinear map. So many of the things that are sort of taken as definitions in the physicist version can be easily justified once we understand the basic meaning, the differential geometric meaning of those entities. We still have a lot more to say about tensors. We have just met 0k tensors so far. We would also have to talk about k0 tensors or even kl tensors, mixed tensors of contravariant rank k and covariant rank l in the old language. And we of course have to talk about tensor fields, 0k tensor fields, kl tensor fields, k0 tensor fields, and so on. But all that is going to come in the lectures which follow this one. Bye for now.